is, yeah, you can speak Dutch. Very good.
Oh, you are trying, yeah. Okay, okay, okay. Are you sure? Because Julia is there. Ah, beh, è Luigi. Va bene, va bene, va bene.
Scusate, potete chiudere lo schermo? Cioè mettere l'altro, grazie. Ok. Da qui.
Oh, I forgot we need to have sound as well. I need an audio.
Okay.
From there.
I think so, maybe.
Serve anche dell'audio dallo schermo. Dell'audio qua. Ci sono i cavi qui? Ok.
alza l'audio del PC podio.
E mettilo anche on screen.
Sì, adesso
Prova a metterlo on screen. Sì.
vado su io adesso. Sì, adesso lo alziamo un attimino, poi voi lo abbassate, ma secondo me questo è già alzato. Questo è se ci
Ok.
colleghiamo a quello. Ok? Allora, l'audio dovrebbe essere su adesso, facciamo una prova.
Allumage Vulcain.
Fallo andare ancora una volta, un pochino più velocemente, cioè più a lungo se possibile. Vediamo, voglio vederlo qui.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3,
Ok, abbiamo testato sullo streaming.
Top.
Adesso potete rimettere la... Ok, a posto. Ok.
sei tu la microphone.
No, basta.
Non urlare dentro il microfono.
Sei proprio tu. Sei proprio tu.
See? Ladies and gentlemen, take your seat. Huh? All right. It's a pleasure and an honor and also a great responsibility to introduce today's speaker, Professor Günther Hasinger, which now is the ESA Science Director. It will probably take half an hour to summarize his CV and his major achievements, so I'll try to be very, very brief. I met Günther in 1992 at MPE, when at the time I was a postdoc, and he was already leading the ROSAT survey efforts in collaboration with Giannis Damorani, among others, and also Joachim Trumper, the former director, and Riccardo Giacconi. Then he moved, and correct me if I'm wrong, to Potsdam to get the directorship, then back as a director to MPE for 6 or 7 years, 8, yeah, okay. And then 3 years as a director of the Institute of Plasma Physics. And then he decided that Germany was too small for him, and he moved to IFA in Honolulu, Hawaii, to take the directorship of the Institute for Astronomy, where he played a key role for the TMT developments. And then probably got bored of the sunny time, and is now back since beginning of this year as ESA Science Director. Günther has done a lot of has got a lot of major achievements in science and also in management, from mainly on AGN and survey in the X-ray band, but also at the longer optical wavelengths. And he also played a key role for the European astronomy. So it's a real pleasure to invite him to give the today lecture. Thank you, Günther.
Thank you very much, Andrea. Thank you to the Institute INAF and the University of Bologna here. I'm really very happy to be here and see so many faces with whom I have had the pleasure to work over many years. And Andrea was my first postdoc, or our first postdoc in the high energy cosmology group in Garching. Andrea has asked me to start the lecture with a memoriam for Riccardo Giacconi, because Riccardo Giacconi was also a very important element in our group. You know that Riccardo discovered not only SCO-X1 but also the X-ray background, and we were the group that was trying to resolve the X-ray background to fulfill Riccardo's dream. And I looked for a photo of Riccardo, and the best photo I could get is actually the one where he was here at the X-ray conference in Bologna a bit less than 10 years ago. As we all remember him, I mean, always arguing, always having great ideas, and he was a wonderful colleague. And I just wanted to review a little bit what he has done, because this is connecting directly into what I wanted to tell today, the synergies between the different elements of the ESA science program. So Riccardo in 1962, originally he wanted to look at the moon in X-rays. That was before the Apollo astronauts were there. And he claimed, we can tell you what is on the moon before you even set foot there. And when he launched his rocket, he indeed found a signal, but it was not the moon, it was slightly away from the moon. It turned out to be SCO-X1, the brightest X-ray source in the sky, and then a whole new era started. But he also discovered the X-ray background, the diffuse emission all around the sky. 30 years later, we were working together with Riccardo, with ROSAT, and we were actually able to repeat his experiment, and we were indeed observing the moon in X-rays. Here you see the picture that ROSAT took X-rays, and the fascinating element was that the dark side of the moon is actually casting a shadow on the background. So this was the first time we could really see that the background comes from beyond the moon. Also, we were pretty sure, but it is not completely true, because when you look at the dark side of the moon, there are some photons, and those photons are about 10 times more than the detector should have produced. And we now know that this is actually geocoronal emission, which happens between us and the moon. And so to resolve and to decompose the different background elements was very important. Rosat then also did this beautiful picture of the whole sky, where you see that it is mainly dominated by hot gases in our own galaxy, but the X-ray background that we are mainly interested in the high energy domain is happening at high galactic latitudes. And there we were actually able in 93 and 98 in a paper together with Ricardo to resolve about 80% of the X-ray background into discrete sources and basically fulfill Ricardo's dream. Even before XMM Newton and Chandra were launched, and then XMM Newton and Chandra made this to a great depth and to a great also coverage in energy band. So those were the first deep images, and then the deepest image with Chandra is now, I think, 7 megaseconds, and the deepest image with XMM Newton is actually led by Andrea Comastri and his group here. So this brings us back to Bologna, where the X-ray background is an important element of the study. With Gianni Zamorani, Martin Schmidt, and others, we then went to optical observatories, both the Keck in Hawaii and the VLT, to spectroscopy of all of these objects and then to resolve them. And the basic message is we are seeing black holes throughout the history of the universe. The whole creation and formation and evolution of black holes throughout the universe is a whole industry now where many, many different people are working. And I just would like to remind that in the active years, in the last active years of Ricardo, in the last 15 years, he has written 54 papers with 5,800 citations, and 31 of those papers were actually with our group with the X-ray background, and so I think his late work was really dominated by, we had the pleasure to accompany him there. And this also led into the Nobel Prize that he got for this whole career. So this is a very nice, I think, background for what I want to tell you about how many different facets are working together, and you are getting synergies out of things that originally were not really meant to work together. And that brings me to today, or to the recent past. Here you see 3 happy ESA directors, the director of science, the general director, and the director of launchers. A few weeks ago in Kourou, where we were actually getting very close to the Ariane rocket, and this was really a very memorable moment. And I wanted you to participate a little bit in that moment. I want to give you a few seconds of the Bepi Colombo launch.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top! Allumage Vulcain. Allumage 2EAP, décollage.
It's really a monstrous undertaking, and if you are standing there and you hear the atmosphere, you feel the atmosphere shaking, and your belly is shaking with you, then you know that there is a 7-ton thing that you have lifted up. And the wonderful experience that we had with Bepi Colombo, it had a very, very long history, very tedious. We had to develop new technologies, new materials. This all took much longer than it should. But now Bepi Colombo is in orbit. And ESA has recently received an award for the Government Agency of the Year, which is given out by the Space News newspaper in the US. So our friends over on the other side of the ocean are recognizing the achievements. The second runner-up this year was NASA. So ESA has actually received this very, very prestigious award. And now Bepi Colombo is in orbit and everything is nominal. I actually had to learn the word nominal, what it really means. Nominal means that you have made a major achievement in both organization, money-wise, in order of technology. Everything works wonderfully. What you see here is a little selfie picture which Bepi Colombo takes of its own solar panels just to show that they are deployed and working. And what is very close to my heart is just 2 weeks ago, the X-ray instrument which is on Bepi Colombo was switched on for the first time. And this is a so-called Deptford X-ray detector, which is a development that came out of the XMM Newton development. And it is a new type of detector which we are preparing to launch on Athena. So it's basically the Athena prototype detector, which is now flying and working in space, and you see the first spectrum of it. And it's particularly important for me because this detector was built when I was director in Max Planck in Garching, so it's a little bit my detector as well. And to see it now flying is really a major relief. Okay, since we talk about prizes, it's very important to know that actually European space science, the European community, and even, I mean, here in Bologna participating are really recognized worldwide. So I already talked about the Space News Award. Our colleague Stefano Vitale, who is also the chair of our Science Program Committee, has received the Amaldi Medal for the wonderful work on LISA Pathfinder, which will lead into the LISA mission. Then you know the Gruber Cosmology Prize. You had a lecture by Nino Mandolesi here in summer, which went to the ESA Planck team and to Jean-Luc Pouget and Reno. The Shaw Prize went to Jean-Luc Pouget, also connected to the Planck mission. And then Evine van Dusseck, who is now the president of the International Astronomical Union, has received the Kavli Prize, and partly for her work with Herschel. And then also something which we are proud of, in our advisory structure consists of renowned scientists, and one of her, Haley, has received the Excellent Order of the British Empire. So just a recognition. I don't really know how to judge how important the Excellence Order of the British Empire is, because the British Empire is no longer existing, but it's still a recognition. Okay, that brings me to the fleet of ESA missions which are out there, which we are operating, which we are preparing, which we have launched. And we have to divide them in 2 slides. One is for the solar system, and the other one is for astronomy, because there are too many to put into one slide. And so here you see the whole fleet of things that ESA has done and is doing in the solar system. Now, if you sort the missions, then the ones in the gray ellipses have already done their wonderful work, like, for instance, Cassini-Huygens or Rosetta, the first and most distant landings that have ever happened. We landed on Titan, we landed on Rosetta, we landed the Rosetta lander, Philae, on the comet Churyumov-Gerasimenko, and Venus, and so on. And the missions that are encircled in red are the ones which we are preparing for the next years. So JUICE, for instance, a big mission that goes to the Jupiter system. SMILE is a small mission together with our Chinese colleagues. Proba 3 is a technology mission which will also do great solar science. And Solar Orbiter will be launched in the next 2 years to go to the sun. Now, there is something missing on this diagram. We are also thinking about small bodies, asteroids, comets, and we are also working together with our Japanese colleagues on Mars moon sample return. And then there is something for the future. If you know the solar system, there are actually 2 important planets missing here, namely Uranus and Neptune, the ice giants. The ice giant planets so far have only been visited through the Voyager spacecrafts in a short flyby, and we don't know very much about the ice giant mission. Sorry, about the ice giant planets. And I'll come back to that because that is a very important theme for the future, to maybe visit Neptune or Uranus and do some real detailed research. Then when we go to the solar system, to the astrophysics missions, here we are sorting them according to wavelengths from the far infrared submillimeter on the left from you out to the X-rays and gamma rays on the right. And again here, the missions that have already done their work are mainly the ones on the long wavelength side. So Herschel, Planck, and also LISA Pathfinder. So unfortunately, right now, we do not have any open eyes in the far infrared, and so we are kind of blind there. And it's clearly that something needs to be done on that side. On the other hand, there is a lot of activity on the infrared, optical, and X-ray domain. We will launch JWST in 21. We are preparing Euclid. We will launch Cheops, which is the dedicated exoplanet mission, Plato, the Planet Hunter, and then we have just today, not today, but this year, committed to launch Einstein, not to launch Einstein, sorry, to work together with the Chinese colleagues on the Einstein probe, and we also work with our Japanese colleagues on CRISM. So the X-ray, optical, infrared side is just really very rich for the future. And if you sort all of those missions into cadence, the green ones are the ones which are active right now, and we have just extended all of our active science missions by 2 years, so we are safely for them to work until at least 2022. And the magenta missions are the ones which we are now preparing for launch, which are already adopted and being built. So Cheops, Solar Orbiter, JWST, Proba 3, CRISM, Euclid, Einstein Probe, JUICE, MMX, Plato. So you are seeing 10 missions which will go up in the next few years, and so it's a very exciting time right now with a lot of activity in industry, in the science community, and so on. I'll come back to that diagram when we talk about the even more distant future. But let me first say that there are these 2 new elements. This year, I'm here since February, so not quite a year. This year we were able to do 5 new missions, selections, and mission approvals. So I'm very happy that this was an extremely successful year for ESA with a lot of new exciting stuff coming. So there is the Einstein probe and the Mars Moon exploration mission with JAXA and Einstein probe with China. And so this brings me to the element of missions of opportunity. So usually ESA is doing the big flagship missions like XMM Newton, or in the future Athena, LISA, and so on. Then we are also doing the M-class missions, which are also quite sizable. But ESA is also doing a lot of activity in partnering with international partners. ESA is actually the partner of choice for many international space agencies. So we are working with Japan, with Russia, with China, with the US. And so the green missions are all the missions of opportunity which we have already implemented, and partly they are still running. Like CRISM, for instance, will be launched in the future, which is an X-ray mission. And then Einstein probe is another X-ray mission, and MMX will bring the first material from a Martian environment down to Earth. And Europe has now partnered with JAXA to do that. So also each of these individual missions is relatively small, but they are broadening the reach and the depth of our science program, and they're very important for the community to survive the big, long gaps between big missions. When you think about XMM Newton being launched in 1999, Athena will be launched maybe in 2030, so you are talking about a 40-year time gap in between, and so it's good to have many smaller opportunities in between. So this is now the plan for the future, and as usual the future is getting more and more uncertain the further it is out, but what you see here is that already until roughly 2030, 2034 or so, we have pretty much defined significant parts of our future. So the big missions, LISA and Athena, but we also have 3 new elements in our future plan. One is the Ariel mission, which has been selected to be launched after Plato. It's an exoplanet search mission. And then the next one is, just a second. Yes, we have also now studied and started to implement a so-called FAST mission. So the idea is that together with Ariel, we want to launch a second smaller mission which we want to run through a very fast process, and we have actually, I'll come to that in a separate slide, we have received proposals for this fast mission, which are very interesting and very exciting. And then we also have installed the M5 mission selection, so we have 3 candidates in the M5 mission, and one of the candidates is very close to your heart, Theseus. So let me come to that. These are the 3 missions which are now being studied in parallel to each other. They are in competition, and in a few years we will select one of these 3 missions. I have to say that all 3 missions for me are very close to my heart, and it will be very hard to select one of them. Ideally, you would like to fly all 3 of them. So the speaker is the cooperation with JAXA to open the eye in the far infrared again to get far infrared sensitivity. Envision is a cooperation with NASA to fly to Venus, to go back to Venus. And then Theseus is clearly also very close to my heart, studying the early universe and in the gamma ray bursts. And it's very nice to know that the original ideas for Theseus and a lot of the activity is actually centered here in Bologna. So that's great. So let me tell you a little bit about the FAST mission call. So when we are launching the next class of M missions and we are using the Ariane 6 rocket, the Ariane 6 is so powerful that it is easy to put a second satellite into the launcher. And since our missions are all going to the L2 point, there is no commercial passenger that wants to come with us, so we want to use that space for a science mission. And so we have issued a call in summer, and we have received proposals in October. And just a few weeks later, we have selected 6 candidate missions that are now asked to submit really detailed phase 2 proposals. And it's very nice to say that 3 of these candidate missions are around small bodies, around asteroids, around the comet. Even what I will tell you in a minute, the interstellar object is part of the mission profile of one of these missions. Then there's a plasma physics mission, and a far UV observatory, and a gamma ray observatory. So we have a very broad spectrum of potential missions that we could fly together with Ariel in the year 2028. And we want to make a selection of the winner next year. And so that will also be excitement for all of us. Okay, now I want to concentrate a little bit on a few wonderful scientific results and achievements that we have seen in this in the last year, basically. These are not only results from ESA missions, but you will see in a minute that there is a very close and tightly knitted web of synergies between these discoveries and what ESA can do. And what I want to start with this guy, the Interstellar Visitor 1I Oumuamua. This has been discovered. Oops! Now we are lost. Sorry. Okay, good. So this has been discovered in Hawaii while I was still director there in October last year. And then I kind of brought it over here to Europe. Oumuamua, why don't you go? This guy doesn't seem to want to work for us. Just a second. Okay, let's try once more. Okay. So it is a rock which is about 400 meters long and 50 meters wide. Nobody understands how this has been formed. Very likely from a planetary formation phase of another star And this object has visited us last October. It came from above, zoomed through our solar system, and when we discovered it with Pan-STARRS in Hawaii, it was already on its way back out. And so we know very little about it, but what we know about it is already fascinating. And so we, for instance, know that it is tumbling, that it is a very elongated structure. It has to be made out of rock, because otherwise, if it is rotating so fast that it would already be slingshotted out. And the most interesting discovery of this year was from Hubble Space Telescope, where Hubble Space Telescope was observing the object until very far out, and they have actually found that the trajectory of this object is accelerating. So it is clearly affected by non-gravitational forces. It is not just pulled in and shot out by the sun, but it is moving away faster than it should. And this is actually the same phenomenon that you usually see in comets. When a comet is coming in from the outer solar system, is heated up by the sun and is moving away, then it's moving away faster than it's coming in. And this is associated with the outgassing of the comet, which is used like a kind of propellant system. But in the case of Oumuamua, there was no comet tail, so people didn't really understand why it should move like a comet. And so you can imagine that a lot of other ideas are around. Maybe it's an intelligent spaceship that has visited our solar system and it is now propelling out again. I don't believe in that, because I think there are a lot of natural explanation. But one of the interesting predictions, if this is a natural object, then we should see one of these roughly every 1 or 2 years. So we are expecting to see the next interstellar visitor next year. And if we can trace them early enough, if we can detect them maybe further out, there might be a chance to even visit one of them with a very delicate spacecraft maneuver. So this is clearly a new field, a new element that we didn't know about a year ago, and which is opening completely new possibilities. And the next thing, Gaia. Gaia is our working horse in astrophysics now. It is completely changing the way we do astronomy with high precision astrometry. And after the new trajectory has been found by Hubble, scientists went back into the Gaia database, and they were actually able to identify 4 possible host stars for Oumuamua. So on the way it came to us, it was passing by about 4 stars, but this is by far not the end of the story, because so far we only have a fraction of the Gaia data with the right amount of information. So in the next few years we might actually be able to see the real host star for Oumuamua. And so we are looking forward for the next Gaia data releases, which will come in about 2 years' time to study this. But just to warn you, every million years this guy is flying by several stars, and each of these stars could actually deviate it from its original trajectory. So it's unlikely that we will really find the true origin of that object. But as I said, it opened a new avenue, new windows in the universe. And so that brings me to Gaia. Gaia has really become our working horse this year. In the beginning, I counted the Gaia papers after the data release in April, and there were about 4 to 5 new papers every day. And it was really amazing to see the productivity of the scientific community which is behind Gaia. This whole year, Gaia has published more than 500 papers and has superseded the Hubble Space Telescope, which was something like 480 or so. So Gaia is now our most prolific mission, and I will come to that in a minute. And an interesting thing is that Gaia is making discoveries of things that we didn't even think about it should do. I mean, the serendipitous work that comes out. And so in particular, Gaia has made an important contribution to the exoplanet studies, mainly by studying the host stars of these exoplanets. And it turned out that the result from Gaia shows that there are probably less Earth-like planets out there than we were originally assuming, a factor of 2 less, which makes the hunt for a second Earth even more challenging and more exciting. And so I want to spend a few minutes about the field of exoplanets, because this is really catching the imagination of a lot of people. And in Hawaii, I have seen that about half of the PhD students that wanted to come to Hawaii wanted to study exoplanets. So it's clearly the field of the future. And so I wanted to give you a little bit also in terms of synergies, what we have done on exoplanets. You know, the TRAPPIST-1 system is a system where you have 7 planets in one solar system, and the sun in that system is very small. It's a red dwarf. And on the other hand, there's also a red dwarf planet close to our solar system, namely in the Proxima b system. That's the closest star to us. And so people get very excited because these might actually be Earth-like planets relatively close to be easy to study. And so, for instance, the Hubble Space Telescope has done transit spectroscopy of the TRAPPIST-1 planets, and through the spectroscopy could show that there is no hydrogen in the atmosphere of these planets, and that means it has to be either a water or rocky surface, and that was confirming that these TRAPPIST planets could indeed be rocky Earth-like planets, and they are in the habitable zone of their star. So everybody got excited and was happy. But I, or some of us being X-ray astronomers, we said, oh, but be careful, because these red dwarf stars are very active in high energy emission. And indeed, XMM Newton has discovered huge flares from the TRAPPIST-1 system. So as we know, the M dwarfs are bombarding their planets with high energy emission, and so it's probably harder for life to develop on these planets. But what I got really excited about was a theoretical study that shows that these stars, these host stars, have very large magnetic fields. And these planets are so close to their host star that they are actually in their magnetic fields. And the magnetic field of these host stars is then inducing a current in the planets. And the planets are then heated up by ohmic dissipation from inside. And it is very likely that these planets are actually liquid planets, lava planets, and not rocky surfaces. So less certain to be able to fly there and maybe colonize these planets. We have to look for better cases. And just very recently, another planet has been found around the next closest star, Barnard star. Barnard star is actually the second or third most close star. And Gaia in the DR3 and DR4 data release might actually be able to see the wobble of Barnard star, which is produced by this planet. So we are looking forward to more exciting data. And just to give you a feeling, this is our the vicinity of the sun. The sun is the yellow dot there on the lower right. And then you see the Alpha Centauri system with Proxima Centauri. And then you see Barnard star very close by. So it's clear that this exoplanet field will keep us very hot and will be extremely exciting in the next 10 to 20 years. And that brings me to the ESA missions, which I already referred to. So CHEOPS will be launched next year. It will do very detailed studies of transits of known exoplanets. Then JWST will be launched in 21 and will do a lot of spectroscopy of the best candidates for Earth-like planets, and it may even see a glimpse of biomarkers or can say something about potential life. And then I think I'm looking very much forward to Plato, because Plato will actually be the first exoplanet mission that can really detect Earth-like planets around solar-type stars. So far, all these exoplanet missions have not really covered enough space to cover 3 years or so of observations. And Plato will actually be able to see planets like the Earth. And so the best chance to find a second Earth will probably be Plato. And then with Ariel, in 2028, we are planning to measure the spectra of 1,000 exoplanets to see something like the Hertzsprung-Russell diagram of exoplanets, so to see how planets are really working in the general sense. And that brings me then back to our own solar system, but before I do that, I just wanted to show you this slide, which shows all the orchestra of facilities that we have to study exoplanets. On the lower part, you see observatories that are doing important science on exoplanets, like Hubble, Spitzer, Gaia, and then in the future, the James Webb Telescope. And in the upper part, you see missions that are specifically dedicated to exoplanets. So starting with Corot, which was a French and ESA mission, Kepler and TESS, which are clearly NASA missions. But then we have the 3 exoplanet missions, Cheops, Plato, and Ariel. And so you see that the center of weight of exoplanet studies will move to Europe. Europe will become, hopefully, the leading field in exoplanet studies. And that brings me to the connection between the exoplanets and our own solar system. So in the studies of exoplanets, we have found that most of the exoplanets out there have masses somewhere, or radii somewhere between the Earth and Neptune. So they are either super Earths or mini Neptunes. And indeed, these 2 classes, Earth and Neptune, are the most abundant of all of these planets. And so you know that we know a lot about Earth, but we know very little about Neptune or Uranus. And that is the motivation to actually, in the future, try to build a mission together with NASA where we could fly to one of these ice giant planets. And if we could do that, then we could do something very similar to that what we did in the Saturn system with Cassini and Huygens. We could fly maybe 2 spacecrafts, either one to each of the planets separately, or 2 spacecrafts that are studying one of the planets in great detail. We could look at the interior of the planets, the atmospheres, the magnetospheres, the moons, the rings, and in particular also the search for origins of life, because, for instance, Triton is an extremely interesting also exobiology world where we could learn more about. So a scientific theme for an ice giant mission is clearly something for the future which we try to push in our strategic vision. Okay, now I come to a field, or come back to a field which I started with, namely cosmology and the violent universe, and what we can learn in the future about the other side of the universe, the very distant universe. And I want to motivate that with one of the most up-to-date cosmological simulations that has been done. Supercomputers became more and more powerful, and now these simulations are actually including not just the dark matter, but also gas. They include the feedback of star formation and black hole feeding processes into the chemical evolution of the universe. And so this is really, I think for a Christmas lecture, this is probably the most fascinating thing to take home. And what you see here is the simulation starts very early in the universe, and the blue stuff is just the dark matter. But then when you look into the centers of these dark matter knots, you will see a red emission appearing, and those are the stars. So the very first stars are formed in the very centers of the dark matter concentrations. And then these stars are evolving. Some of these stars are turning into black holes, and some of these black holes are merging with each other and produce a lot of energy that is flowing back into the universe. And so very soon you will see a whole lightning going on, lightning fire of activity. And here you see something like a supernova explosion, and red stuff coming out. This is hot gas, which is basically pushed into the voids of the universe and slowly pollutes the universe with processed materials, with heavy elements like carbon, oxygen, nitrogen, and so on. And so while the universe started pristine, and the green filaments here are the pristine gas, it is slowly filled, or rather quickly filled, with hot gases and with chemically processed elements. And very soon the whole universe is basically filled with these feedback from the centers of these very close concentrations. And so this brings me to the very important role that mergers of galaxies are playing. And our understanding in the last 20 years or so of this as a crucial process in the evolution of the universe. And these are, again, some of the most detailed hydrodynamical simulations, where on the left side you see the stars of two galaxies merging with each other, and on the right side you see the gas in these two galaxies. And first you see these huge tidal effects where the two galaxies are coming close, and the stars and the gas is basically completely reorganized. But then on the right side of the graph you see the black holes in the center of these galaxies to start their action, and the black holes are actually pushing out the gas with their kinetic energy. And at the end of this process, all the gas is lost into space, and only the stars are remaining. And that is what we call an elliptical galaxy, which has no more active star formation, and only the gas only the red stars are left, and the gas has left this galaxy. So these are theoretical calculations which are supervised by individual observations. But now we can go a step further. Now we can actually go to our own galaxy, and we can decompose the history of our own galaxy using the Gaia data. And that is the completely new element that came this year, where we were able to identify individual stars in our galaxy which are not moving like the rest of the stars. They are moving in opposite direction, different velocity. They also have different chemical composition. And this has actually been interpreted as the remnant of a major merger that happened to our galaxy about 10 billion years ago. And I very much believe that this was the merger which was also then creating the bulge in our galaxy and the growth of the black hole in our galactic center. And when you look at these detailed simulations, this object that has been merged with our galaxy is now called the Enceladus galaxy. And this is a simulation where the Enceladus galaxy in red is encountering our own previous Milky Way, 10 billion years ago, when the Milky Way was still much smaller. And so here you see a Milky Way first, and you see that it is a very narrow disk. It's a very thin disk, but now this merger is coming in, and the red stars are gravitationally distributed throughout the whole galaxy, and they are stirring up the rest of the galaxy. They distribute they deviate the orbits of the stars, and now you see a galaxy with a puffed up disk, and very likely also with a bulge. And these red stars are the ones which we today can still see in our galaxy, and where we can decompose the history of our galaxy with Gaia. And so that just should give you a glimpse of what is now possible with the Gaia data, where this is truly transformational. And as I said before, Gaia has become the most prolific mission with 500 papers every year, or this year. And if you look at all papers that have been published from ESA missions, this is about 10 papers a day. So we talk about 3,600 papers, and this is about 13% of all papers published worldwide through ESA missions. So we really have a very significant impact on the world's knowledge. Okay, and that brings me now back to my own hobby, namely black holes and the early universe. And this is more or less where this is connected to the beginning of the talk, where I was talking about the work we did together with Riccardo Giacconi and others. In the meantime, we have resolved the X-ray background so that there is only about 1% of the background left as a diffuse component. And the same thing has happened in the infrared, where Spitzer has, with very deep images, resolved the infrared sky and has left some fluctuations. And when you are looking at these fluctuations, there's a significant, very large-scale cross-correlation between the X-ray background and the infrared background. And so that must be a population which is very likely connected to early black holes. In particular, we now know that there is not such a correlation between the deepest Hubble images and the Spitzer or the Chandra images. So this is a very interesting population that is only showing up in X-rays and in the infrared, and it is very likely connected to early black holes. Now, in the last year, we also have seen a huge excitement, a huge development about gravitational wave mergers of black holes that LIGO has found, and in particular then one object where two neutron stars were merged. And also there is now a little bit of a discussion whether the LIGO black hole results are really accurate. The neutron star merger is really standing like a rock in there. And so I think that the whole field of black holes has become very exciting again. Now I hope that in the future we can actually use our tools in order to really synergistically study this whole field. I just want to mention that again last year JCMT in Hawaii has found two black holes which are zooming through the center of the Milky Way, which could in principle also be black holes from an early population which are more abundant than we have thought them to be. And so JWST in the next few years will be able to study these early universe populations much better. And then we will get Euclid that will study the infrared sky, and Athena which will study the X-ray sky much better. And so we will, in probably 15 years from now, we will know much more about that topic. Then we will hopefully also get LIGO, which will do the gravitational wave measurements for these merging black holes. And if we are doing it right, we will also get Theseus to study the very early black holes from gamma ray bursts. So this whole multi-messenger quest for early black holes will again, I believe that will be the next field like exoplanets, which will dominate the decade after the next decade. And so we have to make sure from the ESA side that we are really putting all of these tools into orbit so that we really have this wonderful symphony of the whole orchestra of different instruments available. And this now comes to some work of my own, which is still in connection to the X-ray background studies that we have done together with some of you in the cosmos field. I told you that the signal that you see in the X-ray and infrared background is basically showing up in the X-rays and in the infrared, but not in the optical. And so I was looking for X-ray sources in the deep fields that have the same property, that they are basically not showing up in the deepest Hubble images, but they are showing up in Chandra and they show up in Spitzer. And we were able to use much better, very deep observations in the cosmos field based on Hubble, based on Subaru, Hypersur Primecam, and Ultra Vista. And so now we have the best data set available to do this study. And indeed, among 4,000 X-ray sources, I have seen 6 X-ray sources which basically have bright X-ray emission, nothing in the optical, and something in the infrared. And so these could be individual objects of the same type that we see in the early universe, maybe heavily obscured black holes at a redshift of 4 to 5 or so. And so for me, this is a very interesting topic for JWST and then later also Athena to really push on further. So it's very exciting on that field. And so then this is topped off by what I already mentioned, the gravitational wave merger of 2 neutron stars. That happened in August last year, and that has completely transformed our picture of how the elements are forming. These 2 neutron stars were merging, producing a jet, but simultaneously in the center producing a whole zoo of new elements. And today we know that in the chemical period system of the elements, the heavy elements are very likely produced by neutron star mergers, while the lighter elements are produced in the belly of stars. So, you know, we all say we are stardust, but we also are neutron stardust. And by the way, we are also coming directly from the Big Bang because the hydrogen in our water molecules is directly coming out of the Big Bang. So every one of us is representing the cosmos in its entirety. And this has now been enriched by the first discovery of an astrophysical neutrino source, where actually a very high energy neutrino could be associated with a black hole, an AGN in the nearby universe. And so we are opening a whole new field of physics with these astronomical measurements. And it's again, I think, very exciting. And these new windows require really cooperation on a grand scale. These papers that are involved in this physics typically have few thousand authors. And so a significant fraction of everyone in this room is involved in this research, and this is a change in scope that we also have to prepare for the near future. And so that brings me to this last part of my talk, which is actually relatively short, but I think it's very important. How do we convince a society, and how can we convince our politicians and the people on the street who are giving us the money that what we are doing is really important? I mean, it's great to be excited about science and great to be an astrophysicist, but I think we still have a task to do to tell our population, our society, that they really need to spend more money in order for us to be able to do this. And this brings me to this pyramid of innovation and added value that originally Sam Ting has thought of, where on the x-axis you have the different scales, where it starts in the middle with the classical physics of 1 meter, and then on the left side it goes to the small universe, the atoms, the nuclei, and so on. And on the right side it goes to the big scales, planets, stars, galaxies, the universe. And the different colors are the different years. So it starts out in 1900, it goes to 1950, 2000, and so on. And while fundamental research is basically broadening the base of this pyramid, so we are discovering more about planets and stars and galaxies and the universe and maybe even the multiverse. And we also discover more about how matter and physics works in the small scale, and we have discovered the Higgs particle and so on. But applications in society and in economy are actually growing the height of the pyramid. So everything which you see in red here is actually taking some knowledge from basic research and turning it into something which is important for society. Like, for instance, when you look in the central column, we have mechanics, thermodynamics, optics, electromechanics, and then you have the steam machine, you have cars, photography, airplanes, renewable energy, and so on. On the side of the stars, for instance, you use stars for navigation, you use pulsars for timing, and we will in the future probably use the sun for space weather prediction. So our current discoveries are happening at the frontier, where we talk about Gaia, gravitational waves, asteroids, search for life, and so on. But the developments that are then affecting society are happening going upward. And I want to point out two things. Quantum mechanics and relativity have been discovered roughly 100 years ago. And today, quantum mechanics is making roughly 40% of the worldwide gross national product. And relativity with the GPS and Galileo navigation systems makes about 5 to 10% of the gross national product today. And so discoveries that are 100 or 50 years old are affecting our society big time. When you take out your iPhone, you have about 6 or 7 technologies that were discovered and invented for astronomy, and they are now used by everybody. So I think we have to bring this message that it is not basic sciences against applied sciences, it is actually a synergy between the two, and they are working and growing together. And only if you do basic science, you will be able to do economy further down the road. And that is my main argument why we need to increase the activity in space science in the future. And I'm actually asking for, in the next ministerial meeting, which is called Space 19+, for about a 20% increase of the science program. And I will come to you to explain why that is necessary. But if we would get this 20% increase, then we can also promise something to our politicians and to our society. One idea is that we would try to launch the big missions LISA and Athena, which originally should be launched one after another, But if we get a little bit more money, we will be able to pull them together so that we can launch 2 big missions at the same time, which is absolutely necessary to do this synergy between, I mean, the sound and the movies. If we get this extra increase, we will be able to fly to Neptune or Uranus, so we would have this unique, it's actually turning out that there is a unique celestial opportunity where in the year 2030, Neptune and Uranus are behind Jupiter, and so you can actually fly to Jupiter and you get a gravity assist to Jupiter so that you can get easier out to Neptune and Uranus. That's the same trick that NASA has used for the Voyager spacecrafts 40 or 50 years ago, and now we can actually do that again in the next period. And F missions, and also helping the member states to build the more and more complex payloads. So this is a package where we say, if you give us 20% increase, we promise that we will deliver more content, and you can also be proud of us. And so the top kind of catchy phrase for this is bringing sound to the cosmic movies, where we try to fly Athena and Lisa together. And I'm very happy to say that both Lisa and Athena have made huge steps forward in this last year. The technology is getting more and more mature, and I'm really optimistic that we can pull Lisa forward, and hopefully we could also pull Athena about a year forward, so to do everything faster if we are getting this extra money. And I was very happy to see that already in the published literature there are a few people who have made very detailed calculations and simulations about synergies between Lisa and Athena. So when you have 2 black holes which are merging, then they produce gravitational waves. But for a long time it was not clear whether they would also produce electromagnetic waves, because the gravitational waves are so powerful they could actually push out the baryons around the black holes. But the more detailed relativistic simulations of both matter gravitational waves together show that actually a very strong X-ray signal is expected when 2 of these supermassive black holes are merging. And if it is possible to catch the merger early on, and the right diagram, it's a bit complicated, but it shows that this should be possible in quite a number of cases where Lisa is detecting the merger about a year before it happens. And then Athena could look at the Lisa error box and try to identify the guy who is starting to merge. And then we could follow that merger, and then we would see X-rays and gravitational waves basically ringing hand in hand, and we could also see something like a chirp in X-rays, which would then nail down the gravitational signal. So very exciting, and a lot of younger people in the audience will actually be able to see this. I think we are already getting beyond our horizon in that domain, but we are still committed to make that possible for the future. And so I'm very happy to report that a few months ago in ISAC, in my home institute in Spain, we had a ministerial meeting where the science ministers of all the member states or their representatives, the secretaries of states, heads of delegations came and unanimously approved a number of resolutions what we should put into the proposal to the ministers next year. And in particular, resolution number 2, providing strategic guidelines for the preparation of the agency program, very strongly focused on increasing the science program and increasing the mandatory program for ESA. And so here you see the ministers and their representatives, and the sentence which is above there, which recognizes the importance of the mandatory activities and underlies the objective to secure an adequate level of resources so that the scientific program will continue to build on its remarkable success in the past years, while giving consideration to increasing the financial resources made available to it so that it can do more science activities. This has been unanimously underwritten by the ministers, and this is the hope that I can cash that in a year from now into, as I said, a 20% increase of the level of resources. And with this hopeful outlook, I would like to thank you all I would like to just quickly show that this increase of 20%, which is shown here on the right side, is actually compared to the growth of the national product of the ESA member states quite small. So we are rebuying more or less the buying power of the science program that we had during the times of Roger Bonnet. But this is a much smaller fraction of the GDP than it was previously, so I think it's justified to ask for more if we want to keep the leadership in Europe. And we are actually going into a major new planning activity where I want to skip over this diagram, it's a bit too complicated, but we have set up a committee that is actually helping us to define the future, the cosmic vision until 2050, where the level of resources that can go in there is a crucial element. And so we want the young generation among the scientists to help us defining the next 25 years of successful science with ESA. And so with this, now I would like to send you off to a wonderful Christmas season. Buon Natale, buon anno, and come back with even more energy than you have today. Thank you very much.
Thank you so much. Thank you, Gunther, for this energetic talk. So, question, curiosity, please.
Yes, so please, if you have questions, I'm happy to answer a few. No? If not, okay. Massimo.
Actually, it's a simple question. When do you plan to have this new Cosmic Vision 2050 written down and decided?
Yes. So we have just identified the committee. The chairs are Linda Tacconi from MPE Garching and Chris Arich from Imperial College. They are representing astrophysics and solar system science, and we have now. Yesterday I sent out the nomination letters for a total of 10 people in the committee. And the first meeting of the committee will be in January 22nd. And then they want to send out calls for white papers to the community to come with ideas. And in parallel, we are also starting a social media engagement campaign where we ask the kids on the street about their dreams, what they want to see in the next 25 years. And that should all kind of culminate roughly in September next year, shortly before the ministerial meeting, so that we can bring an important message to the minister. So we hope that this will be done in about 3/4 of a year. Reno.
Yes. So in this period of economical crisis, global economical crisis, I think this is true. Is there an attention from ESA to small missions? I mean, nano satellites, micro, and whatever small satellites.
Yes, so I talked about the F mission, the FAST mission. And we have just issued a call for these FAST missions. I had one view graph there. We have received 24 proposals, and we have now selected 6 candidate missions for a small, fast mission. And then in addition, we are also doing these missions of opportunity, where we are joining forces with smaller countries like Japan, China. So we are actually broadening that. There are 5 new missions which we have identified this year, where we are broadening our basis and are also enabling more things than just the big missions. Yeah, even smaller missions. For instance, the F mission has an acute idea. Some of these F missions are using a spacecraft to send, for instance, to a planet or to a comet or something like that, and then they carry small sats, CubeSats or so, and then you can actually release a swarm of CubeSats around that distant object, and then you can use the mothership to use for telemetry and because if you go to the solar system, you need pretty much power just for the telemetry, so you need a big antenna and so on. So you need something big, but you can actually have small satellites that are like a swarm around the big mission. So that's one of the ideas.
Often space missions need ground-based support. And there is a special ESA policy for that, or the issue is left to each individual project?
You mean ground-based in the sense of telescopes, or in the sense of funding for science? No, telescopes.
Eventually both, but especially telescope.
Yeah. So in the case of Euclid, for instance, we have a huge ground-based support component which is provided by the Euclid Consortium. So ESA does not really control that, but it is part of the, similar to how the member states are providing instruments, they are also providing that ground-based support. In the case of Plato, we are actually planning something more agency-wide, where we are starting to negotiate with ESO, whether we could do a big community call for follow-up science on Plato with ESO. So both of these things are in principle in the making.
You had told us about synergies between, say, fundamental science and exploration, solar systems. So what are connections eventually between science missions and exploration missions, science landing on the moon, landing on Mars, say humans or other celestial bodies?
Yes, so you know ESA has a directorate for science, which I'm the director of, and then there is a directorate for human exploration and human and robotic exploration. And the HRE is mainly focused on objects where in the future humans can go and work, so to speak. So HRE is mainly focused on the space station, on the moon, and on Mars, while the science program is focused broader, so we land on comets and so on where no humans will go there. But on these bodies like the Mars, for instance, there is a very strong synergy. So for instance, we have Mars Express, and we now have also the ExoMars mission, which is in principle an HRE mission, but we are now running it as a science mission in order to do the science of TGO. In parallel, ExoMars is used as a relay station for NASA rovers or ESA rovers for the ExoMars rover mission. So there is an overlap. An interesting case is the case of Mars sample return, where the human spaceflight and robotic exploration directorate is very interested in building up an infrastructure on Mars to do the sample return. So they have several rovers, some are doing the digging, another rover is bringing all the samples into a cave where they basically store them for 10 years, and then there's another mission in the 2030s coming and collecting these samples and bringing, so it's more in terms of the logistics and the infrastructure than purely the scientific interest. Whereas the Japanese, for instance, they have a very clever way where they don't land on the object, but they are just basically sniffing material up, what they are doing with Hayabusa 2 now, and which they are also planning with the MMX mission. So with the MMX mission, they are planning to fly to Phobos and Deimos, which are the Martian moons, and there they bring material back to Earth. Now, the Martian moons are not Mars, and it's not clear whether they are really made out of Martian soil, so to speak. They could also be asteroids that Mars has collected at some point, so they could be completely different from Mars. But on the other hand, There could also be Mars material that has actually been ejected from Mars after an asteroid impact and has landed on Phobos. So when you bring stuff from Phobos back, there might be some Mars material as well. So there are two different approaches. Mars sample return is really a huge infrastructure involving 20 years of activity with several different rovers and a lander and a relaunch capability. Whereas the Mars sample, the MMX mission is basically just about sniffing some material and bringing it back to Earth. So we are involved in both. MMX is run by our directorate, Mars sample return is by the other directorate. But whenever the HRE directorate comes into a realm where they are focusing on science, then the science program is actually taking over. So like in the case of ExoMars, where we are now running the TGO mission as a true science mission. So it is a difference in focus on one hand, but it's also a difference in funding mechanism. The science program is a mandatory program, which is defined by you, by everybody in a bottom-up process. The HRE program is an optional program where governments define what they want and what they fund. And governments, I believe, are more interested in the kind of logistics, economic aspects of this enterprise. And the science for them is, so to speak, not the main driver, because they say the science is done in the mandatory program.
Very, very interesting your talk, and the only question I see in the planning of the satellites by ESA is the long time required from the earliest proposal to the launch. I don't know. One time, 5 years, 7 years was a typical time. Now I see, if you see, requires something like 15 years, which seems very, very long, and this could be a negative effect.
So actually for the L missions, it is more like 20 years for the large missions. And the main reason for that is that there is a lot of technology development necessary in order to go there. You know, all of the science missions have to be in several parameters much better than their predecessors. We are talking about, for instance, XMM Newton versus Athena. We want to have at least a factor of 10 more effective area, but the costs are more or less the same. So Athena is roughly costing the same amount of cash that XMM Newton cost. And that is only possible by major technology development, which takes time. Like, for instance, the Athena mirrors, we just had some breakthrough this year, but we are not yet there. We need another 2 or 3 years before we really know that the Athena mirrors can deliver what they can. In the case of LISA, LISA Pathfinder was already a very expensive and long mission and proved that the gravity drag-free measurement is possible. But one key element for LISA is the laser. We need a factor of 10, 20 more powerful laser than we have today, and it has to work stable for years in orbit. So that's something which is not existing right now. In the case of the M missions, the timescale is more like 10 years. So we have selected Ariel this year. We launch it in 28. So we need about 10 years after the selection before we do the technology development and the adoption. We realize that this is very long, and therefore we have instituted these F missions, the fast missions, which are hopefully doing this whole thing in 7 years or something like that, instead of 10 years. But it is a very long time scale, and it is not because we are not working very hard. It is just inherent in the whole system. It was easier in the past, where you were doing things for the first time, and you were able to take risks and so on. But now every other step has to be better, significantly better than the previous step. But it has to happen, you don't have an infinite amount of time and money, so it all has to work together. Sorry. Okay.
There are many undergraduate and young graduate students. Do you have any recommendation for their career? The final one?
Yes. First, when you look at my career, it was not straightforward. It was like a winding road, and I was very often kicked out of my path and was doing something else. So don't shy away from thinking out of the box and doing something that your neighbor has not done. And the second advice is, if you want to achieve something, you have to aim higher, because it's always easy to go lower, but it's very hard to go higher. So if you want to do an academic career and you want to stay in science, better shoot for a professorship and not for just a researcher.
Thank you. Thanks.